In this video you will see two examples of how we can do calculations when we're applying the law of conservation of momentum. This by no means is covering all of the cases. I'm just using two simple cases of elastic collision, so no energy is being lost due to some damage done during the collision or lost to heating up the system. So again, this won't cover nearly all of the cases of collisions, but it should give you enough guidance so that you can do the problems which I'm assigning with this particular unit on conservation of linear momentum. So here on the board we're going to be considering an ice skating situation when we have a little boy with a mass of 50 kilograms and let's say his grandma with a mass of 80 kilograms, and they're on an ice skating ring, and somewhere on the ring they're going to collide. Hopefully in this case let's say it's going to be an intentional collision, so either the boy is going to intentionally hit the grandma or the grandma is going to hit the boy. We'll consider two different cases. One case is when one of them is stationary before the collision happens, and the other case is when they are both moving before the collision happens. So in the first case, let's say that the boy is moving toward the grandma, and his velocity, his initial velocity, is going to be 3 meters per second. 3 meters per second. And let's say grandma is just standing. She's just standing on the ice, and she's just extending her arms and welcoming the boy. And as soon as he hits her, she just grabs onto him, and then together they continue to move. Or at least that's what the law of conservation of momentum tells us, that if the momentum before the collision was not zero, then the momentum after the collision should not be zero, and they in fact should be the same. So we can say that momentum before collision equals to the momentum after the collision, and the general equation would look like this, that we have the momentum initial of both of them added together should be equal to the final momentum of the two together. So the subscript I stands for initial, and the subscript F stands for final. So we can say that the initial momentum of the boy, so I'm going to start putting the numbers in. So the 50 kilograms times his speed, which was 3 meters per second. I'm going to drop the units just so that we don't have to write so much. Plus 80 kilograms of the grandma times 0 meters per second. That should be equal, after the collision, we're going to have, again, 50 kilograms of the boy times the velocity after the collision, which we don't know, plus the 80 kilograms of the grandma times the velocity after the collision. And those two velocities are the same because they are moving as one object. The grandma just grabs onto the boy and they continue to move with the same velocity. So we can write this to be equal to, we can factor out the velocity. So 50 plus 80 times the velocity, And on this side right here, 80 times 0 is 0. 50 times 3 is 150. 150 equals 50 plus 80 is 130 V, and so we can calculate V, the velocity, to be 150 divided by 130. 150 divided by 130, of course, in meters per second. Meters per second is going to be 1 point something. 1 point whatever decimal would come here, meters per second. And you can see that it's the same, it has the same sign, the velocity has the same sign, so plus. Here the velocity of the boy was plus, so that means it's happening in that direction. So after the collision, they both continue to move in that direction to the right, with the velocity being given by the ratio of 150 to 130 meters per second.